In a previous video, we saw how to deal with one type of nonlinear model where we have a square dependency. What we learned is if you have something that looks like a parabola, that upward swooping curve, there's a good chance that if you square the horizontal axis variables and replot, you will get a straight line. Today we're going to look at another nonlinear model that often pops out from experimental data. This model we're going to look at today is called an inverse dependent model. And hopefully as we get through this presentation, you'll figure out why it's called inverse dependent. So again, we're asking ourselves the question, what if a line isn't a good model? Always we want a line to be our model, but sometimes it doesn't work out that way. And again, we need to consider that sometimes you're just not going to be able to get a good model because the data is just too random to make a predictive model out of it. But sometimes it's not. And we'll take a look here at an example that comes from some real-life data. This is the length of a string, like a guitar string or a piano wire, any kind of a musical instrument that has a string, and the frequency of the sound that comes from that string. If you gather this data, which is shown here, and then you plot it, you find out that probably this is not a linear relationship. We can see that there seems to be some other kind of a pattern going on here. If we do a regression analysis, linear regression, we find out that the r-squared value and the r value are not really great. And definitely if the numbers go beyond the range that we have on the graph, we're probably going to deviate a lot from that best fit line. Because this isn't just random, we have a pattern that shows this kind of a downward swoop. Now it turns out that there's more than one kind of mathematical model that fits this general pattern, but we're going to look at one of the really common ones that we see often. So to look for this math pattern, we're just going to look at some numbers rather than data and look for a pattern in this generic data. Take a look at this data. Can you tell what the pattern is? Here's a hint. It might be helpful to think about the y values as fractions and not as decimals. What you may have noticed is that all of the y values are 1 over the x values. 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3, which 0.333 is approximately 1/3, and so on. So that's the pattern. When we plot this, we get that characteristic shape, that kind of downward swoop. And so that gives you some indication that maybe that's the pattern that's going on here. Now, what would happen if we took 1 over x and we plotted it against the y values? So on the horizontal axis, instead of x, we put 1 over x, but we leave y up here. Well, what we'd have is the horizontal values would be equal to the vertical values. And so you'd have a line with a slope of 1. So what you did there was created a line by plotting a different look at the x values on the horizontal axis. Take a look at this one. Can you spot the pattern? You may have noticed that this is just 1 over the x values times 2. 1 over 1 times 2 is 2. 1 over 2 times 2 is 1. 1 over 3 times 2 is 2/3, which is what 0.667 is. So that's the pattern. It turns out that this is going to follow that same shape, and once again, if you were to take 1 over each of the x values and put that on the horizontal axis and y on the vertical axis, you would again get a straight line relationship. But that straight line relationship just won't have a slope of 1 like the previous example. So this is a pattern that can be linearized by just taking 1 over x and plotting that on the horizontal axis and leaving y the same, leaving the vertical axis the same. Let's go back to the example and see if it works here. In the pink row, I have taken all of the lengths and divided 1 by them, and I have the data there. Plot it. It certainly looks like it did straighten out the line, and a linear regression tells the same story. The r-squared values are very, very good, round to 1 in fact, so that would be nearly perfect. And so now we have a linearized mathematical model. Take a look at the values here. Horizontal axis is 1 over length, vertical is the frequency, and this is our mathematical model. you can predict the frequency by taking 1 divided by the length, multiplying it by this constant number, which is the slope of this line, 21,400 hertz over 1 over centimeters. That's a complicated unit, which could be simplified. We'll do that on the next slide. And that will predict for you what the frequency would be for that string. So this is the cleaned up version. 1 over centimeters is the same as centimeters, so the unit simplifies to hertz times centimeters. So again, you take 1 over the length, multiply by that constant, and that predicts the frequency. So now we have a working model for this relationship. So let's summarize. Before we do this, I want to reiterate a disclaimer that there's more than one mathematical pattern that kind of looks this way, but this one is very common, and we'll see it more than one time as we investigate things in this class. If you have a pattern that looks like this, one of the things to try is to replot with 1 over the independent axis variable on the horizontal axis, and then leave dependent variable alone. And if that works, if it turns into a straight line, then the relationship is the dependent variable is equal to a constant number, which is the slope of that new transformed graph, times 1 over the independent variable. So now we have 3 ways to deal with experimental data. If it's an obvious line, and the regression analysis shows us that it's a good model, a line is a good model, well, we can just use the equation of the line as our mathematical model. We now know that if we have a parabolic shape, the upward swoop, then it is possible for us to transform the data by taking the square of the independent variable and plotting that against the dependent variable. And then the slope of that becomes a constant, where the dependent variable is equal to that constant times the square of the independent variable. And now we know that it's quite possible that if we have a downward swoop, that's called a hyperbola in math, that's an inverse dependent relationship, and if plotting 1 over the independent variable gives us a straight line, then the relationship, the mathematical model, is the dependent is equal to a constant number times 1 over the independent. That's an inverse relationship.